In this video, I want to give you a few examples of how to incorporate equilibrium into mass balance problems. Instead of giving you really specific examples, what I'm going to do is give you kind of some generalizations so that you have some idea of strategies for solving a multitude of problems. So the first thing I want to do is give you an example of a problem where we're combining a mass balance mixing problem with some sort of equilibrium. So if I were to, just kind of sketch this first example, this is a mixing with equilibrium. So here in this problem, we've got two streams, 1 and 2 mixing to form this third stream. I'll go ahead and just kind of call this a mixing point A, because this is a very important mixing point for our problem. When you first see a problem like this, let's say you weren't given this diagram, you might be pretty surprised to see these flows and concentrations being the same as here. So what I've done here is I've assumed that our particular system is going to be at steady state. Okay, so even though, let's say maybe the water would, or whatever, the fluid was shut off, this particular, whatever it is, tank emptied, there was nothing in here. You might think, because I find that sometimes when you're thinking about problems, you're thinking about startup. So you might think, oh, well, once fluid starts flowing here, there's this head space, this vapor space right here. So that is going to be increasing in concentration, and so this C would be lower than this C because you're losing some of whatever C is to the headspace, which would be true on startup. However, let's say this has been going for quite some time. The liquid is totally in equilibrium with the space, with the headspace, and so it's not losing any more than it's not losing any additional C, whatever C is, to the headspace in this steady state problem. So we have both a steady state system and this is totally in equilibrium. And so here we're going to say this headspace has a partial pressure of C, PC, whatever that happens to be. So looking at this, there are a few things we can do. So one of the first things we might consider doing is doing a mass balance around A. Okay, and then we can do a mass balance for whatever the carrier fluid is. We're assuming that there are no density changes when I write the equation like this. And then we can also do a mass balance for whatever C is. You're also going to want to figure out, let's say maybe you were asked what this equilibrium concentration was. So whenever you see equilibrium between a liquid and a vapor phase, you know that you're going to need to use Henry's law. So we have, whatever our KH is for this compound C is going to be our concentration in the liquid phase in the reactor. Remember, this needs to be in moles per liter, divided by whatever the partial pressure of C is. And then kind of depending on what you're asked, maybe you need to convert that partial pressure to something else. Or maybe you're given the partial pressure and you need to figure out what C3 is, or maybe you even need to go back and figure out what C1 or C2 is, depending on what the question is. What could our reactor be? So there are several things this reactor might be. Maybe it is a tank with a sealed headspace and you're interested in the equilibrium with the headspace. It could be a tank in a closed room. And maybe it's something like cyanide, where that has some sort of vapor pressure. You need to be pretty careful about that. It could be like a strong acid, like hydrochloric acid, which would also go into the headspace or the vapor phase. And so you'd really be concerned if that vat of hydrochloric acid was in a closed room. So these are kind of like OSH type problems, so occupational safety and health problems. Maybe you're looking at a manhole, right? So this could be a manhole. You've got sewage flowing through it, and maybe you're concerned with H2S and hydrogen sulfide in the manhole. So these are all different kinds of situations where you might be applying this particular type of problem. So the second type of situation I want to do is a mixing problem after equilibrium. Again, this could apply to kind of similar situations. It might also apply to a situation where you've got maybe gas bubbling through a liquid. You could also think about, so rain is very often going to be in equilibrium with the atmosphere. So you could have a situation where V1 is actually rain here. And so this is our reactor. We're going to say some sort of gas is added, gas bubbled. Or it could be a situation where it's rain and it has some partial pressure. And then we have something coming out that now has some concentration and equilibrium with the gas that was bubbled through the reactor. And then that's going to be mixing with something else to form this third stream. Okay, so you have this sort of situation where you've got this mixing point. I'm still going to call it A. After some sort of equilibrium situation happened here, maybe it's a tank, maybe it's an equilibrium with the atmosphere, maybe it's an equilibrium with some other sort of like headspace situation. Okay, so again, we're going to do an equilibrium here. In this particular situation, I'm looking at gas and liquid, so we're going to use Henry's law. So some sort of KH applies to this situation. Remember, C1 is going to be in moles per liter, and this is going to be the partial pressure of C. And then again, we can do a mass balance at point A. So if our densities of 1, 2, and 3 are all the same, we can simplify the flows like this. And then do concentration, or whatever C happens to be. Okay, so kind of a similar situation, but to our first example, but we have mixing afterwards. You'll see that a lot of the equations are all the same as we had in one. I guess the big difference here is if this is the tank, then our concentration before and after the tank is the same, whereas here, if the whatever C is totally coming from the gas, then we would have, maybe we assume no C in V1. Okay, so for this third kind of set of equations, I want to just kind of talk about general chemistry questions, or questions that are going to involve chemistry. So, maybe this is equilibrium with alkalinity. You could also think about equilibrium with some sort of hardness question, etc. So I think a lot of times with these types of questions, you might be wondering to yourself, do I even need to think about equilibrium, right? So maybe the question just says something about, alkalinity, and it mentions the pH, and maybe it gives you some other information about the concentration or partial pressure of something, and you're like, I don't even know if I need to to consider equilibrium. Okay, so I have given you two tables. One has KH, Henry's law constant, and one has pKa's. So, and those are the tables that you should look at if you just have no idea. If you don't know where to start. So I'm going to go ahead and pull some of those over. And with time, you're going to know. You're going to have a better intuition of like, oh, like, is this a type of reaction that's going to happen or not? But for now, you might not have that intuition. And so if you have a problem where you're like, hey, you know what, maybe I need to think about equilibrium, maybe I need Henry's law constants, but I'm not really sure, you can always just look at these tables and see if any of the compounds that are in the question are also in these tables. And that's a good place to start, right? So if you have, N2, nitrogen gas, that does go into water pretty well. And we've got that Henry's law constant here. Same is true for acid base. So maybe you've got a question with phosphoric acid, H3PO4. You can look at this table and see, oh, so H3PO4 dissociates, becomes dihydrogen phosphate, H2PO4. That dissociates, becomes hydrogen phosphate. And then that dissociates to make phosphate. So you can look at these tables to start building your knowledge of types of, like equilibrium that you might have between things dissolved in water and vapor, and then also the types of acid-base equilibrium that you have in certain situations. So for example, arsenic, right? So that has acid-base reactions that might be important. So so look at your questions, and then if you do see chemical compounds listed, you have an inkling, maybe there's a pH, maybe you've got a vapor phase, you're like, maybe I need to think about this, but I don't know what the equations are, you can always go back and look at those tables. For the sake of this class, either you will find them in the tables or I will give you the equations that are important. Okay, so consult the tables. Let's say you've got a question with alkalinity. I think for me personally, and what I would recommend to you is if you just don't really know where to start, just write down the equations and look and see what's there. So our simplified alkalinity equations that we're going to use for this class includes bicarbonate, carbonate. Okay. So already looking at this, you see that pH is really important. If you can't remember something, right? So this is going to be calculated from pH. And if you ever are kind of like, like, what do I do here? I have included basically something called the chemistry toolbox in your class notes. And you can always go to this to look for hints to solve these types of problems. So we've got just general equilibrium, Henry's law, acid base. Those are the only kind of equilibriums we're doing in this class. But I've also got these equations for finding, well, in this case, H plus from pH. You just take the 10 to the negative pH to get H plus from pH. Remember, we've got our self-ionization of water. So pH plus POH is going to equal 14. And so you can calculate all of these things from just the pH. So you know those if you're given the pH. You might be like, oh, maybe these are involved in equilibrium reactions, and you would be correct. So you can go to your table, you see, okay, I've got bicarbonate here, it's in equilibrium with H2CO3, and then carbonate is in equilibrium with HCO3 minus bicarbonate, and that's where you can start. Okay, So I'm going to go ahead and write those down. So we have, in this particular table, they don't actually give you the chemical equations, right? But basically they're telling you that carbonic acid is going to lose its hydrogen, become bicarbonate, HCO3 minus, and this is the pKa for that equation. So you can take that information and construct the following, which is H2CO3 star, carbonic acid, loses a proton, becomes bicarbonate, and the Ka for that is 10 to the negative pKa, which is 6.35. Okay, and we can do the same. Bicarbonate loses a proton, becomes carbonate, and the Ka to that is 10 to the negative, that's going to be 1 and 2, 10 to the negative pKa, which is 10.33. Okay, so you can construct your equilibrium equations with that information. Ions are never going to evaporate. So if you are looking at a series of chemical compounds listed, none of these ions, bicarbonate, carbonate, hydroxide, H minus or H plus, anything over here on this side, none of those are going to enter the vapor phase. This carbonic acid, H2CO3, however, is not an ion. That of everything listed here is the only thing that you would need to check on the Henry's Law table. And indeed, if we go to our Henry's Law table, we see carbonic acid right here is number 1, and that's going to be in equilibrium with carbon dioxide. So I could write that equation down. And remember again, this star means that it's both carbonic acid and also aqueous CO2. So, and then we have a KH here. So, you know, a lot of times you might run into this problem of, oh shoot, what do I do with this H2O? And the thing is you don't include it in your equation, or you could include it as 1 for KH. So that is another thing that you always want to remember. If you do ever have water, liquid water, don't include it in your KH equation. Okay, so whenever you have problems like this, you know, it starts to get really complicated really fast. And so, you know, you can write down a whole bunch of equations, but you might also want to consider, if you're given the pH, if you can eliminate any terms. So in other videos, I've showed you a graph that looks, you know, something like this, which you can make graphs that look like this if you're given C total, if C total is fixed. A lot of times if you're doing some sort of analysis and you have, you know, like a closed sample, C total is fixed, that's not going to like change if it's in a closed file. You know, if you have equilibrium happening between the atmosphere, and then you've got acid-base reactions going on, pHs are changing, C total isn't really going to be fixed as your pH is changing. You would still have potentially compounds, or like that first term, so your acid form would still be like interacting with the atmosphere. But if you've got like a fixed C total, then you can draw, you know, you can sketch this like this. Oh, this is horrible, but you have a better one in another video, right? Where Oh, I can't handle it. I gotta do it again. Okay. This is gonna be 0.5. These are gonna be your pKa's. Remember, you've got 1 for every proton that you can lose. So if I have 2 pKa's, I'm dealing with a diprotic acid. This up here is going to 1.0. Okay, and I can use this as a guide. And that's going to help me. Oh, no, it doesn't actually help me at all. Okay. And so this is your most acidic form over here. And then this is your most kind of like basic compound with no hydrogens at all. Okay, so you don't necessarily need to draw these if you want to be thinking about pH and eliminating terms. So if, let's say, we're dealing with a carbonate system, sometimes I just sketch, because I'm a very visual person. We've got H2CO3, carbonic acid, in equilibrium with bicarbonate, and also carbonate. I know that this pKa is like 6.3, this pKa is like 10.3. So if I've got a pH, whatever, really low pH, let's say our pH is 3, I know that it's mostly going to be carbonic acid. If our pH is 12, I know it's mostly going to be carbonate. If our pH is 8, I know it's mostly going to be bicarbonate. And so you can look at the pH. Let's say the pH is like 3. You can be like, yeah, well, you know, like there's not really much of either of those, so you can cross them out. So that's totally a way to quickly visualize your system if you're given the pH and cross some terms off of, like for example, your alkalinity equation. If it's actually asking you for something like you know, HCO3, you're probably not going to want to just cross that term off of your acid-base equilibrium equation. But you should totally feel free to cross it off of, or you know, to cross something that's going to be really low off of that alkalinity equation. So remember this. This is a really nice sketch to kind of keep in your back pocket for different systems. Okay, so carbonate, really important for environmental engineers. I also want to look at sulfur dioxide. So maybe, you know, like it's very important in acid rain. But let's say you've got a problem with sulfur dioxide. You don't know what it does. Okay, so our first step, sulfur dioxide is a gas. So we'll check the KH table. When we do that, we see, oh, look, it's number 2. We see this equation right here, so it becomes H2SO4. This particular table doesn't tell you what that is. It is only listing the gas right here, SO2. But if you're looking at that, you see some H's over here. It looks kind of like an acid, and in fact it is. That's sulfuric acid. We also see this star, which means the exact same thing as it does for carbonic acid, that it includes that dissolved SO2. Okay. Okay, so this looks like an acid. Maybe you don't remember that it's sulfuric acid. So what you can do is you can go to this table, H2SO4, sulfuric acid, and it has a pKa of -3. Okay, so you might be like, whoa, what does that mean? You remember back to chemistry, strong acids and bases. -3 is a very, very low pKa. It's a strong acid. It loses its hydrogen, and it becomes bisulfate, H2SO4. That still kind of looks like an acid, doesn't it? It still has that H. And indeed, if you go down to the next line, you see HSO4 negative right here, bisulfate. It has a pKa of 2, and then it becomes sulfate. No more hydrogens. You know that's as many acid-base equilibriums that you're going to have to consider. So we've we've suspected that it's an acid. We go ahead and we check the pKa table. We see that, in fact, it is. Actually, I'm not going to write aqueous on all of these, but they are all aqueous. Okay, and this is another situation where these are really low pKa's. So you know that if you've got a high pH, the concentration of H2SO4 and also HSO4 is going to be really, really low. If you've got a high pH, let's say a pH of, 4 or greater, 4 isn't even really that high, 5 or greater, whatever, most of this is going to be in the form of sulfate and not bisulfate or sulfuric acid. Okay, so the last thing I want to do is I want to show you kind of a situation where you've got equilibrium and you need to use the continuity equation. And remember, this is going to be v dot equals the velocity times the area. Okay, so let's just say we've got some sort of volume. Okay. Okay. And, maybe we even just know, like that's some, like length x and y. We have some sort of velocity going here. Same velocity going over here. So maybe this is a tank that you're given the dimensions of. It could even be, if we flipped it 90 degrees, you could think of this xy as a plane falling at a rate of v. Let's say we're bubbling gas with some partial pressure, or the rain, v, could be falling through the atmosphere, and that could be the partial pressure of something in the atmosphere. So if you're given this sort of situation, right? So this is going to have some sort of concentration. Again, you've got some sort of gas, you've got something in a liquid. You need to use Henry's law, but you're also going to have to use the continuity equation. So you've got the continuity equation, v dot equals dA, which would also be, in this situation, vxy. You're going to have to use Henry's law, probably, because you've got gas and liquid. So our KH is going to be Cg. Remember, that's going to be in moles per liter over the partial pressure. And then maybe you're like still not quite sure, right? So maybe you want to check the pKa table to see if there's anything else that's going to be interesting to you. Okay, so that brings me to the end of this kind of like just hodgepodge of examples of problems that you might see that incorporate both equilibrium and also concepts from mass balance. So first we did mixing with equilibrium, where we had kind of a mixing problem that led into a problem that required some equilibrium concentrations. Then we did a mixing after equilibrium, where we had a situation where we had equilibrium with a gas and liquid phase. Maybe you've got a tank with bubbling. Maybe you're looking at rainfall. Rain is in equilibrium with the atmosphere. And then we had a mixing problem. We also talked about just some strategies for solving questions that incorporate equilibrium, right? So maybe we're looking at alkalinity, which could also include something like a mixing problem, where we can get our hydroxide and our proton concentrations from the pH. We looked at our pKa table. Remember, ions don't go into the vapor phase, so you're only going to need to check your non-ion species. We looked on the Henry's law. We looked at a pKa table for additional information. And we talked about looking at pH and seeing if we can eliminate terms from, for example, our alkalinity equation. If the pH is indicating that there isn't much of that compound given the pKa's. Then we did an SO2 sulfur dioxide example, and we kind of mined information from those tables with that example. Finally, we did an equilibrium kind of example with a continuity equation, incorporating both this idea of the continuity equation where we have the velocity and the area or dimensions, and we have to incorporate that into a Henry's law problem. So hopefully this has given you a broad overview of types of big problems that you might see that you can apply different mass balance principles and also principles of equilibrium.